So we're going to be talking today about lecture 00 in the syllabus. I mean, we're not officially starting yet, but I figured I'd do some preliminary stuff that might help you guys with what we'll be doing in the course, because this class does involve proofs. It's not going to be all about computations. I do expect you to be able to write mathematical arguments down when talking about certain things. So I figured very few of you are math majors. Some of you probably aren't familiar with proofs at all. So I figured I'd give a lecture about proving things in general, and some things that I probably expect you guys to know, but you might not know it. It's in no way meant to be comprehensive. You're not going to just become an expert at proofs just by listening to me, so don't have that expectation. But for those of you who have seen proofs before, I expect this to jog your memory enough to be that you can just move on with it. And for the rest of you, it should be some sort of starting point for when you're writing your own proofs, as we will be doing throughout the semester. By the way, this book is available in the tutoring center. I think they have several copies there. But I think a nice book to learn proofs from is called Mathematical Proofs. By Jhevon. I probably put this in the syllabus if I don't remember. Mathematical Proofs, A Transition to Advanced Mathematics by Jhevon. I think it's a very well-written book. And if you took a course like Thorough here, that's usually one of the standard texts that they use. But I think it's very well written for what it is, and you might use that to supplement what I'll be telling you here. So let's actually get started. Crash course on proofs. Don't seem to be work very well. Need to do some thicker markers. First, let's talk about statements. What is a statement? So when I use a statement in this class, it will mean a declarative mathematical sentence. By the way, what declarative means. These markers are horrible. What declarative means has exactly one, what we call truth value. So it's true or false, right? There are no other possibilities for the statement, right? So when I say there's a mathematical statement, it's just something that is either true or false. It has to be one and exactly one of these two options. So it cannot be both true and false, and it cannot be neither true nor false. It has to be either true or false. These are mathematical statements. So for example, 2 is even is a statement. It can be true or false, right? 17 is even is also a statement. It happens to be a false statement, but is a statement nonetheless. If I say x is even, that is not a statement. Why?
X doesn't have a value.
X doesn't have a value. I don't know what it is. It could be true, it could be false. There's no way to be sure. It's not declarative, right? So this guy is not a statement. However, if I said something like, if x is an element of 0 plus or minus 2 plus or minus 4, then x is even, that's a statement. Now that's declarative. Now I can be sure whether that's a true or false statement without any ambiguity. So that's what a statement is. So declarative mathematical statement, declarative means it has one truth value. It'll either be true or false, not both, not neither. Okay? Uppercase letters often represent uppercase letters often represent statements. From now on, for the rest of this lecture, if you see me write uppercase P, uppercase Q, uppercase R, these are statements. They would represent some mathematical sentence that is either true or false. Definition. If P is always true, it is called a tautology. Another definition. If P is always false, it is called a contradiction. Okay. 1 plus 1 equals 2. This is something that I can prove true or false. It is actually always true. It is a tautology. If I say a differentiable function is not continuous, that is a contradiction. Or 1 plus 1 equals 3, it's a contradiction. We'll be using contradictions later as well. Creating and combining statements. So given some mathematical statement, you can create bigger mathematical statements, and you can combine mathematical statements. Okay? So if P is a statement, this symbol P is its negation. A negation of a statement has the opposite truth value. In all instances. So it's literally going to be the statement that whenever P is true, it is false. If P is false, it is true, etc. So if I can have P, I can write this down in a truth table. This is what's called a truth table. I can say P can be true or it can be false. There are no other possibilities. If P is true, this is false. And if P is false, this is true.
Can you say again, please?
Huh?
Can you do again?
This is called negation, and if you're writing this down, you'll refer to it as not P, right? Meaning P is not true. Meaning, whenever P is true, it is false. Whenever P is false, it is true. It will always give you the opposite truth value, and we call it the negation of P. So there are so-called also conjunctions. So given two statements P and Q, the statement P and Q, this is written like P with a little caret Q, is the conjunction. This from now on, I'll kind of, just to save time, I'll kind of just write down the truth tables and let that kind of speak for itself, because a lot of times you want to think in terms of that, especially if you're just starting out. So on a truth table, if you have P and you have Q, P and Q, this just means it's true only when both P and Q are true at the same time, right? So you can go through all of the possibilities. This describes all possible combinations of the truth values of P and Q. Here they're both true, so it is true. In this case, Q is false, but P is true. This is false. In this case, P is false, but Q is true. This is false. And in this case, this is false, and that is false, this is false. So that is how the truth value of P and Q will behave, depending on the truth values of P and Q separately. There's also something called the disjunction. We also have P or Q. This is a statement that is true when either one of P or Q or both is true. So the notation for this is P with a little v, Q. This means P or Q. So here's P, here's Q. This is P or Q. All possible combinations here. So here P is true and Q is true, so one or the other is true. Here P is true but Q is false, that means P or Q is true. Here the Q is true, so that's true. Here no one is true, so that's false. Another very important statement is we also have the so-called implication. It's a very important kind of mathematical statement because a lot of things in math depends on the assumptions you're making. So this has in symbols, this is P implies Q. This is red. P implies Q. Here's its truth value. P, Q, it's truth table. P implies Q. Does anyone actually know what this looks like? Yeah?
True, false, true, yeah.
True,
Only false.
false, true, true. Right? This is called the implication. Another way it's read is if P, then Q. There are many mathematical statements that will be like this. So you could say something, for example, you've seen statements like this all the time. If a function is differentiable, then it is continuous. That is precisely this kind of statement. And I can say things like, if a matrix has determinant 0, then it is invertible. I'll be saying statements like that. And that is called an implication. The only time an implication is false is if P is true and Q is false. Yes?
What about if P is false and Q is true, then Q doesn't follow from P, right?
What?
Like,
No, a false statement implies anything. If the first statement is false, the overall statement is automatically true.
So if it's a false statement, if P is false, then Q can be anything.
You can do whatever it wants. This is called an implication. One way you can think of it as, probably a nice way to think of it as sort of a contract between two people. If you do this, then I will do that, right? The only time that would be a lie is if you did something and I didn't do it, right? So if you do this and I follow through and do what I said I would do, I told the truth, right? If you don't do what I asked you to do, then I didn't lie whether I do it or not, right? Because you didn't fulfill your end of the bargain, so I'm not at fault, right? So that I'm okay in either case. The only time I would be telling a lie is if I said you do this and I do that, and you did it, and then I didn't follow through on my end. That's the bad one. Okay, so one way you can think of it as a contract. If something happens, then this will happen. The only time that statement is false is in the case where the first thing happens but the second one doesn't. So a false statement would imply anything. So mathematically or logically speaking, I can say, if 1 plus 1 equals 3, then pigs fly. That is a true statement. Because if we're in a universe where 1 plus 1 equals 3, then why not be in a universe where pigs can fly? Yes?
What about the contrapositive?
Yeah, I'm getting there. I'm listing off a bunch of statements. I didn't say these are all the possible statements yet.
Okay. This one is, the other one was called conjunction. This one is
Disjunction. But you can just think of it as or. I'm not going to quiz you on this. Oh, this is name this kind of statement. I just want you to be aware. It's okay to remember this sentence. Right? Describe it as a sentence. There's also something called a contrapositive. Or, well, I don't actually want to introduce that yet, because I want to introduce that in a context of a proof. We could do something that's called a by implication. These are equivalent statements. This is P. The arrow goes both ways. I would refer to this as something like P if and only if Q. Or I can refer to that as P if with two F's, Q. Right? So if I do that, that's not a typo or a misspelling. It's on purpose that I wrote two F's. And how you can think of this is a conjunction of the implication going both ways. This is really, this is P implies Q, and at the same time, Q implies P. Now I can give you the truth statement for that right away, but let's actually build up to it so you can kind of see the exercise here. P, Q, P implies Q, Q implies P, and then P if and only if Q. Here it's true, false, true, false, true, true, false, false. So now we look at P implies Q. Literally the only time this is false is when this is true and that is false. So that's here. And then everywhere else it's true. Literally the only time this is false is when this is true and that is false. Which means that's here. Everywhere else it will be true. And now this, meaning P implies Q and Q implies P, both of these have to be true. This is the same caret here. So what would this line look like?
True, false, 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 true.
You can notice that this happens 2 times. It happens when they're both true or when they're both false. This means they have this truth value at the same truth value all the time, right? Meaning that you can think of these 2 statements as equivalent statements. If me saying one is the same as me saying the other and vice versa. Right? If one is true, the other is automatically true. If I say something like, the following are equivalent. And I list statements, 1, 2, 3. And I list the statement P, I list the statement Q, I list the statement R. This means that P implies Q, Q will imply R, and R will imply P. You will go in a cycle. The order does not matter, but you have to go through the cycle. So if you start with statement P, you have to go through all the statements and end up back at statement P. And that means the following are all equivalent statements. They'll all imply each other, right? Because you'll see that P implies Q, but if you start at Q and go through the chain, eventually it will imply P. Same way you'll have P implies R, but if you start from here, R implies P, right? They'll always go in both directions. You'll always go through a cycle. And the following are equivalent means so this statement is the same as saying all statements are true, or, and this is an exclusive or, all statements are false. I.e., if one is true, then all are. If one is false, then all are. So if you have equivalent statements and you want to prove something based on an equivalent statement, knowing any one of them means you know all of them. These are called equivalent statements. It's a group of statements where they'll all be true at the same time or they'll all be false at the same time. You can't have some of them are true and some of them are false. So we can call those equivalent statements. Let's look at quantified statements. Okay. There are two main quantifiers that we will care about. There's this symbol, which means for all, or for every, or for each, something similar to that. There is this, which is a backwards capital E. That means for some, there exists or for at least one, something, etc. So I can say something like, for all x in R, x squared is greater than 0, right? This is me making a quantified statement. I'm making a statement that applies to everyone in a certain set. I could also say, there exists an x in R. Or I can say there exists an x in R such that x squared is greater than or equal to 0. Right? This means it will happen for everybody. This means it happens for at least one person. Both of these happen to be true statements. So those are called quantifiers. How about negating statements? Let's do some common ones. you'll have to know how to negate an implication. So this means here, if I have P, I have Q, that P implies Q. Right? This is true, false, true, false, true, true, false, false. This here would be false here, but true everywhere else. What would the negation look like?
False everywhere, true.
False here, false here, false here, true here. Does anyone know what kind of statement would give such a result?
Do not parentheses P implies Q.
Yeah.
Not P, right? So every time P is not true, this is, well, let's complete this because I have to complete it for that to make sense. Not P,
Implies not Q.
Well, you can say implies, yeah, like not Q. Implies not Q. No, but you don't have those two.
Wait, can you just negate the whole?
yeah, that's what I want to do.
Why not
I can
P
do
and
the
negate
whole thing?
this.
Why just negate the whole thing?
So why not?
Just like it
Not
comes around.
parentheses.
Huh?
implies
P
Q.
implies not Q. Can't you do that?
What would P implies not Q look like?
Oh, it'd be false on
It'd be
the
the
top
same
line
thing,
and then
but-
true everywhere else.
Yeah.
Yeah, never mind.
I want, this means equivalent. I want an equivalent way to say this. There's a way to say actually without an implication.
Isn't the inverse just not P implies not Q? Isn't it the same as the inverse?
Right.
Not P implies not Q.
Yeah.
It's kind of like distributing the not.
But you won't get that. You won't.
Or you can use it with the or.
You can do, there's a way to do with or. How do you do with or?
Q or not P. Or something. Yeah.
But can you think of a way to say this with an or?
What about P and not Q?
This you can write as not P or Q, right?
Oh.
What do you think the negation of something like that is? This is true precisely in the cases if P is either false, which it counts for these two, or Q is true, which counts for this one. This one has neither of those fulfilled.
P and
P and
not
Wouldn't it
Q.
be and so?
P and not
P and not Q is the right way to do it. Okay? That's going to be important later. Do you know what law I applied to do that?
Moore's law?
Huh?
Moore's?
It's called De Morgan's law.
Moore.
This is called De Morgan's laws. De Morgan's laws are the guys that tells you how to negate and or. Right? Basically, this is the law that says if you negate something and something, that's the same as saying negating this or negating that. And if you negate something or something, that's the same as negating the first thing and negating the second thing. These two are called De Morgan's laws. Knowing how to negate something would be useful when you're doing something like a proof by contradiction. So you need to know how to define different statements. Let's say I wanted to negate a quantifier. If I wanted to negate something like, for all P, we have Q. Let's say I make a statement like that. How would I negate such a statement?
For every.
The negation of this. Negation of for all P, Q.
Would it be
Yeah.
the E for
For some, there exists for at least one.
So, I mean, there exists a P such that
It's not Q.
not Q. Right? That's what that's equivalent to. In other words, the negation of for all is there exists such that not that happens. Right? So I could say something like, for all x in R, x squared is greater than or equal to 0. The opposite of that statement is there is some x in R for which x squared is not greater than or equal to 0. Right? That's the opposite. Right? So if you're saying something happens for everybody, the total opposite of that is no, there's at least one person for which that doesn't happen. Okay? Similarly, if I wanted to negate there exists P such that Q, there's at least one example of this thing. What is the opposite of saying that? For all of this, that will not happen. Right? You can't even find one person for which that would happen. Right? Now technically you're talking about a specific individual when you say here, so technically it's P of X, but I mean, I want to just give you the general gist of the idea. Don't want to get too bogged down in the theory. This is a crash course after all. And we have lots to get to. Okay, what else? Closing statements. Okay, let's talk about some proof techniques. Proving P implies Q. Right? That, as I said, that's a very important kind of mathematical statement. There are many mathematical statements that can be written in that form, or you can rewrite them to look like that form. Okay, so being able to prove such a sentence will be important. One way is called what we call the direct proof. This is the guy that says to prove P implies Q. 1, assume P is true. 2, show Q is true as a consequence. Step 2 is incredibly difficult, but it's really only 2 steps. It talks about the approach to which you're going to prove statements. Let's do an example. I'm going to define something for you. Let n be an integer. We say n is even if n is equal to 2k for some k an integer. I just defined to you for what an even integer is. It's just the double of some other integer. We say n is odd if n is equal to 2k plus 1 for some k in an integer. Right? You'll notice that that can break all the integers into 2 groups, all of which are either odd or even. So you'll notice that 0 plus or minus 2 plus or minus 4 plus or minus 6 plus or minus 8, blah, 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 they can all be written in that form. And plus or minus 1, plus or minus 3, plus or minus 5, etc. can all be written in this form. Okay? So now here's a statement. Prove let x be an integer, then if x is even, x squared is even. This is an implication. In this implication, this is my statement P. This will be my statement Q. So a direct proof says we assume P is true. So let's pretend x is even, and then we need to show that Q is true as a consequence. When you need to show something is true in this class, you have to refer to some definition. Right? You can't just say, oh, well, I guess so, or something like that. It's always going to be referring to a definition. You have to assume that if P has the characteristics of being an even number, you have to prove that Q also has the characteristics of being an even number. This definition is what's going to fall back on you. And that is going to be a general piece of advice for the entire class. You need to know your definitions, not kind of know them. You need to know them precisely and mathematically. You need to be able to usually write down a formula, write down a sentence with a very specific way of ordering the words, very specific way of using the words. Definitions will be very, very, very important. So when I write down a definition, you have to know the definition, you have to memorize the definition, you have to memorize it in exactly the right way, and you have to memorize it in such a way. If you don't want to use my exact words, but I recommend that you do, you have to memorize a statement that is equivalent to that, meaning the truth values will line up all the same in the truth table. Okay. So so proof here would be assume x is even, right? So we start by assuming that the P statement is true. Then what can we say if x is even? Yeah?
Since x is even, square is even.
Then x is equal to what? What?
I was gonna say, since x is even, x equals 2k.
Yeah,
Right.
it's okay.
I thought I heard someone say x squared is even.
Yeah, I see.
Well,
Okay, so I should probably mention that. Okay. Don't really write this, but let's say you say, if x is even, and you start to think about, okay, 2 is even, I square that, I get 4. Okay, 4 is even, I square that, I get 16. Yeah, this is even. Yeah, it seems to me that if x is even, then
but 3.
x squared is even, right? Because you thought of a finite amount of examples in your head or whatever. What kind of mistake is that called? It has a specific name. This is called begging the question. What means begging the question? This means assuming what you need to prove. You need to prove to me that x squared is even. You can't just say x squared is even. That means you're telling me something as if it's true when that's what I asked you to prove in the first place, right? So this means assuming what you need to prove. Right? You cannot write the statement down. You have to justify me that you're able to write the statement down. You have to justify it somehow. Okay? Okay, so let's restart this. But that was good. That I probably actually forgot to mention begging the question. It's actually a very common mistake. Okay, so proof. Assume x is even. You need to remember, first of all, what that phrase means. Then, x is equal to 2k for k at some integer. Okay, so that's what it means to be even. This means, what can you say about x squared? It's going to be 2k squared equals 4k squared. Now what can you say?
It's 2 parentheses 2k squared, so that's another constant, therefore it's e.
And this is an integer. So I'm able to write x squared as 2 times an integer. So this is equal to 2l, where l equals 2k squared is an integer. This means now you can write the statement x squared is even. And you can end the proof like that. Right? One thing I want you to be aware of is to say a statement, I need to make sure that that object fits a particular definition. Yes?
Can we, instead of saying like, like n equals to 2k, we just like say it out loud, like anything times 2 will always become even. So, would that work instead?
No.
Or, okay, just want to make sure.
Would it be like for all real numbers?
No. Saying a random real number is even wouldn't apply. You can't say pi is even or odd. These are only, so that's again, a definition is very important, like all the parts of the definition. So I didn't write this statement down because I felt like it's important to the definition. And that's another thing that's very important is that if I give you a definition or I give you a theorem, it's very important that you do not assume anything that's not written there. Okay? So I wrote this down and I said let n be an integer. Don't think in your head, it's probably okay for it to be a real number. No, if it was okay, I would have said n can be a real number. You understand? Don't assume something that's not there. That's also very important. Okay. There's no reading between the lines. I know in human communication there's all this reading between the lines. Oh, he said this, he probably means that because he wanted to be polite. Math is not that way. You will always specifically say exactly what you mean. Yeah.
We are sort of assuming though that integers are closed under multiplication.
Yes.
I have a question.
And I just want to kind of get through this proof, but normally in a math class that's building up everything, to say what Z is, they would have defined it. Z is a set that has these properties. It's closed under multiplication, it's closed under addition, whatever. Z is, yeah, Z is such a set. Yeah.
Why is it that 2k squared would be an integer and not the 4k squared? So
Why could you not stop here? Yeah?
It's not a
Still-
form of.
The definition has a 2.
yeah.
It's wrong to stop where there's a 4. To prove something is true, it has to fit exactly to a definition.
So the k doesn't matter because the k over there is to the first power.
No,
and
the
you're
point is you need to be able to write it as 2 times something that you know is an integer.
I understand.
We know that 2k is actually 2 times k times k.
Right.
You would have known that if you multiply two integers, you get another integer. So this you would know is an integer, which I can call L. 2L is exactly the form as 2k.
Thank you.
Yeah. So that's the very important thing. Right? So you're going to have to be very OCD, very pedantic, very specific, or it's incorrect. Yes.
So we can say it is an implication.
This whole statement is an implication. This is an if-then statement, right? Because it starts with an if, and then it gives you another statement. Okay, so this is an example of a direct proof. Right? And you can't prove something is a certain kind of object without referring to some definition. So at some point, I will define things for you. I'll say, this is what this means. And at any point after that, if I say, prove that this is this kind of object, you need to make sure that you can make that object look exactly like what I said in the definition. Okay. So if there's a constant in that definition, it has to be that constant. If there's a letter in the definition, you can write some other letter, but make sure that letter has the same property as the letter in the definition. So my letter in the definition is an integer. So I need to, whatever I'm replacing with a letter needs to also be an integer. It needs to fit this exact definition. The definition has a 2, it has to have a 2. Right? It's not okay to stop at the 4. Okay. This is good. Keep asking me questions, because these are things I probably wouldn't have said because I'm kind of rushing through things. But it's good for me to actually be answering some of these questions. Let's go to another kind of proof technique. Like I say, it's a crash course. We're really only doing one example. There's something that's called a proof by contrapositive. So in a proof by contrapositive, to prove P implies Q, the first thing you would assume is you would assume not Q. So if I give you an implication, assume that the second sentence is false. 2, show not P as a consequence. Right? This works because P implies Q is actually an equivalent statement to not Q implies not P. Meaning, if you write out the truth tables for both of them, they give you exactly the same truth values at exactly the same time. I should probably also mention, this is in red, stronger red, green. I don't know if that's going to show up. P implies Q. I'll just, these remarks make it hard to emphasize stuff. Okay. P implies Q is not equivalent to Q implies P. Right? So just because I mention a statement in one order, it does not mean the statement is true in the other order. We can actually talk. So if given this statement is called its contrapositive. This is the contrapositive. Of P implies Q. This guy is called the converse of P implies Q. So given an implication, the converse is not always true. A nice example from calculus is about continuity and differentiability. It is true that if a function is differentiable at a point, it is continuous at that point. It is not true, however, that if it's continuous at a point, it is differentiable at that point. And the generic example is absolute value x at the point x equals 0. You are continuous at x equals 0, but you don't have a derivative there. You can't draw a tangent line there. So just because something is true in one order does not mean it's true in the other order. So that should also never be your assumption. So if I give you a definition and the definition has the form of an implication, do not assume that the definition works the other way, unless I specifically say, you know what, it also works the other way. Never assume something that is not written there. You have a question?
Well, yeah, it might be a really dumb question, but like going back to the truth.
Yeah. I don't expect anyone to be familiar with this, so all questions are.
Going back to the truth table, you could have, in the case of P implies Q, you could have a not Q. Oh no, if you had not Q, you had to also have not P in order for the thing to be true.
Yeah.
But you could also, okay, so that's why it
Yeah.
needs to be.
I mean, actually do it as an exercise. Just on your own time. Actually write out the truth tables for both of them. You'll realize
Because
that.
if you assume that Q is true, it could be either not P or not.
Yeah.
Or yes, P.
Okay. So this is called the contrapositive. So sometimes sometimes a sentence is easier to work with if you think of it the other way, but you can't just flip it the other way. You have to negate the individual statements in order to remain logically equivalent. So for example, I can say if x squared is even, then x is even. So I turn the previous sentence around. It happens to be true in both orders, but that's not all the time. A couple things I want you to consider here. Suppose we tried a direct proof. Okay. What would you start with? What would you assume? You'd assume x squared is even, right? That would mean that x squared is 2k, for k is an integer. Where would you have gone from there? Right, you want to make a statement about x. To get x from this, you'd have to actually take a square root. Now, good luck proving that that is 2 times an integer plus 1. You would actually run into trouble, right? You also the pluses and minuses, and with a radical there, and you know that radical 2, for example, is not an integer, how would you know that it fits the definition? You would actually, you wouldn't know what to do. So it turns out working with the last statement would be a lot easier, because it's easier if you have something to square it and you know what you're squaring is an integer. But if you take something and you square root it, you can't be sure it's an integer. Right? You can't be sure that it will fit that definition. So a direct proof would be a difficult thing to do here. But we can know that that is an equivalent statement. And so this allows me to work with the last statement in an implication as opposed to the first statement. So if you want to prove something and the first statement is really difficult to deal with and the last statement is easy to deal with, a proof by contrapositive is what you try, not a direct proof. So instead here, I would start the proof by assume x is what? Odd, right? As in I would assume x is not even, right? All integers are either even or odd. Then, what does that mean?
X is equal to 2k.
X is 2k plus 1 for some integer k. So,
X squared then use 2.
x squared would be 2k plus 1 squared, which is going to be 4k squared plus 4k plus 1.
And then we was
2 parentheses 2k squared plus 2k plus 1 at outside.
Right? This, I assume that if I told you about an integer, I would have told you that that's also an integer. So this becomes 2l plus 1. That's exactly the form we want. And L is an integer. This means that x squared is odd. I want you to recognize that that is actually not p. Right? P was the fact that x squared is even. This is not p. X squared is odd. That's where you want to end this proof. That's called a proof by contrapositive.
Professor,
Yes.
shouldn't we add we are proving the original statement like contrapositive at the end, or no?
That'll be okay. Start out with the opposite of the first statement and with the opposite of the last statement. You don't have to use the statement to summarize it. Oh, this shows that. That's okay.
That was my question.
Huh?
That was my question.
Okay, yeah. By the way, the above two proofs show that x squared is even if and only if x is even. Right? So if you had to prove these, you would literally have to show both the proofs that I showed before and put it all in one gigantic proof. Right? So to prove this, you would start off the proof like that would usually be like what you write. First show that I'm proving in this direction, and then write proof 2. Then, if you draw the arrow in that direction, you would write proof 1, and then you'd end the proof. Right? You have to show that it works this way and it works that way. So those are two very common ways to prove implications. Another common kind of proof is a proof by contradiction. To prove P implies Q, you may show that not P implies Q would imply a contradiction. So what would that mean? Step 1, you would assume the negation of the implication, which it's hard to actually write that down without using the other equivalent definitions. What did we say this was? P and not Q, right? That is literally to assume the negation of that. Show that a contradiction occurs because of this. and you have free reign here. You can literally prove that a contradiction happens somewhere in math because of you making this assumption. It doesn't specifically even have to do with the statements involved here, although it often will, but it doesn't have to. Why does this work? Well, C is always false, right? So if I actually prove an implication that says R equals C is true, this would mean R is false, right? But if I say the negation of something is false, it means the original thing is true. So that's why a proof by contradiction would work. It all goes back to the truth tables and you playing with logical symbols. But R is the opposite of what we want here. I'm looking at this as the statement R. So here's an example. Prove there is no smallest positive real number. By the way, that you could write as an implication. This is equivalent to saying if x is in R and x is positive, then there is y in R such that y would be less than x. It's the same kind of statement. So you could phrase it as an implication. On a lot of mathematical statements you can do that, but we won't even do that here. What you can do here is just assume to the contrary. Or assume for the sake of contradiction. You can start off your proof like something like that. That there is a smallest positive. I'm going to call this number x. So pretend, you know what, I think there's a smallest positive real number. Let me call it x. What can we say? Some of you probably have seen something like this before. What would you be able to say? You can literally break something else in all of math. Something you want to take advantage of. What do you think? Yeah?
Consider x divided by 2.
Consider x divided by 2. Half of a number is always smaller than the number. Then x over 2 is actually smaller than x. And furthermore, x over 2 is also positive since 2 is positive. So we've found a smaller number. And that's a contradiction. Right? Lightning strikes, the earth swallows you up. Right? So I made an assumption. Yes, there's definitely a smallest guy, but then you're like, oh, I found someone smaller. And like, okay, let this be the smallest guy. Divide by 2 again. Oh, I found someone smaller. Right? You'll never be able to say this statement and it always means true. It'll always break because division by 2 makes you smaller if you're positive. So that's an example of a proof by contradiction. I'll just mention trivial and vacuous proofs here. This is the idea that P implies Q. Given P implies Q and Q is true, then we know P implies Q is true. Right? Because if you look in the truth table, the only time this guy is false is if Q is false. So if you know for sure that Q is true, the whole statement is actually true. Right, so I can say if x squared is even, then 1 plus 1 equals 2. I'm just making something stupid. You can literally write down as a proof here, you can say the statement is true, and you say trivially. And that would be your answer. So if you have something like this and you know for sure that the second statement is true, or you can prove that it's literally always true, you can prove that it's a tautology, for example, then the implication is always going to be true. You say that's a trivial proof. Like you literally don't have to do anything, it's trivial. Yeah?
Could we say the same thing about the first question you asked? If x is true, x squared is even. Can we use that proof, the trivial one, to prove that?
No, you couldn't do that.
Because you said if the first statement is true, the second one would be trivial.
If x is
Even. X squared is even as well.
x squared is even,
X squared might be off.
X is even.
It's only the
But, I mean, we're
yeah, but how do you know the truth value for this?
Because if x is even, the power would be even too.
2.
And the power-
Yeah, but you're assuming this, not that. I made a statement about q. We know about q.
Alright. I see the point.
So you don't. If you know about x, that's not saying anything about this. So you actually don't know about this. You couldn't do that.
So let's use direct proof for that one.
Well, yeah, we actually did this. This is an example I did. Yeah, I would have used a direct
Yeah.
proof. Yes.
For contradictions, does it prove the statement is true or false?
The original statement would be proven true.
Yeah, so this is not contradiction.
What do you mean?
This is counterexample, not proof by contradiction. Because we proved it's wrong.
All right.
This is not a counterexample.
Wouldn't it be just counterexample if we just show the last statement? Because we proved it's wrong, we didn't prove it's true.
Well, what's a counterexample?
We give something that disproves.
A counterexample is when you give a specific example. I
Yes.
didn't give a specific example. I in fact proved that you can't, it's impossible to actually find a specific example. It'll be true in all cases. That's different from a counterexample. A counterexample is a specific thing. Right, so like if someone says, oh, all prime numbers are odd. A counterexample would be, here's the number 2. It's prime and it's not odd. You can give me a specific statement to disprove a general statement. That's called a counterexample, right? But if you write a general proof and construct a whole argument and get to something, it's not a counterexample. Yes?
Trivial proofs are only really good for tautologies then, right? Because
It's if you know the second statement is a
yeah,
tautology.
if you already know that Q is true.
It's either you know that it's true, this is a tautology.
Yeah.
It's either you know it's true, or you can kind of see that it's easy to prove that it's always true. So if and usually it's going to be a statement that you can see. So if someone says x squared is always greater than or equal to 0, and you know if x is in R or something like that or whatever.
So you can just take the opportunity to do a direct proof that Q is true, and therefore just say the whole thing
Yeah.
is true.
Yeah, but you kind of have to see it. It's something you have to have like knowledge about. In terms of vacuous proofs, this is when P is false. P implies Q will automatically be true. So if I say if 1 plus 1 equals 3, then pigs fly. You can say the statement is true vacuously. You don't really have to do anything in a trivial or a vacuous proof. Once you can prove either that the last statement is always true or the first statement is always false, then the overall implication will be true according to the truth table. Tons more proof techniques here. Yeah, there's no way I'm going to get through induction in 3 minutes. Yeah, so I want to talk about proof by induction, proof by cases, and disproval. In which case I'll talk about the counterexample versus when you don't want to do a counterexample. Yeah.
Are those two practical? Like, are we ever going to see those in class?
Well, no.
Okay.
Well, we are doing linear algebra. So specifically speaking, the topics that I'm mentioning here, no, we're not going to see them. We're going to be talking about things like matrices and vector spaces and blah, blah, blah. So I'll give you statements about those. But I'm giving you these guys because you guys know about even and odd integers. I don't want to use anything.
Sorry, I meant like the trivial and vacuous proofs. Like, do those ever, like, I don't know, I've had some experience with proofs and I feel like I've never done ones like those.
Really? I've seen.
I've said quantum truth table.
Sometimes you'll know. So for example, let's say you can say something like, if x, y are elements of R2, so like x plus y equals 17. 2x plus 3y equals radical 2. Now, let's say I gave you something like that, right? And that's a very generic statement. You might actually go through and do a lot of work in actually solving this guy, but the numbers might be ugly or something. Like I put the cube root of 3 or something like that. However, as a linear algebra student, you'll be able to recognize that the coefficient matrix of this system is something like 1, 1, 2, 3, right? And you'd also be able to recognize that the determinant of this is not 0. So a theorem that we'd use in linear algebra would say that it literally does not matter what numbers you put here, there will be a solution. And so literally whatever this sentence was wouldn't have mattered. So that's an example. Right, but that's more like a little bit of linear algebra thrown in there. We will talk about determinants and when a determinant is not 0, what it means, or what a determinant is. For a 2 by 2 is just this number times this number minus that number times that. So this guy would be 3 minus 2. So the determinant is 1, it's not 0. And that actually can tell you something about a system of equations with those coefficients. So I literally could have said any gibberish right here, and you would say this is true trivially. Right? 'Cause that's always true, so whatever, the whole state, it's all true. So we're not done with proofs, but I don't think it'll take the whole of next class. So we'll talk about induction, another very important proof technique that we'll use all the time, and some other goodies. And maybe I'll talk about also where matrices come into the picture, and then we'll start the actual syllabus. We will have a quiz on Tuesday on the things I've spoken about so far. Yeah.
For your website, the password doesn't work if it's capital, it works if it's lowercase.
Okay. So if you're logged into the online homework, it has to be lowercase. There's actually already online homework. I think it's due for next Friday. So make sure you can log in.
The quiz is
Hold on.